Hello. It's been in the news that Donald Trump's company, as a private citizen, has invested in nuclear fusion. This investment the president did, or his company did, as a private citizen, does not involve U.S. funds, just to clarify that. But enough of politics and economics. The question is, maybe some of you have, is what exactly is nuclear fusion? Interestingly enough, nuclear fusion really isn't all that different from what happens when a fire burns, although maybe you think it is. When a fire burns, you're fusing together atoms to form a molecule. You're fusing together one carbon atom and two oxygen atoms, and they come together to form a carbon dioxide molecule. Carbon dioxide is another interesting chemical that's been in the news a lot lately because people have been concerned about global warming and how burning stuff, be it petroleum or coal or releases, could increase the carbon dioxide content in the atmosphere. So that's also been making news. Fusion. What is fusion? Fusion, we're fusing together not the entire atom, but just the nuclei of the atom. Much, much smaller. The atom's like a huge thing. Nearly all its mass is in an area, tiny area. It's almost like if all the mass of the Earth were in like an automobile, and the rest of the Earth were just all the clouds in the sky. I mean, that's kind of, science is kind of interesting that way, but really, nearly all the mass is in like a part that's only like about 1,000 times smaller in diameter than the entire atom. And if you want to talk about volume, well, volume is the diameter. It goes as like the diameter times the diameter times the diameter. You gotta divide it by a few contents, like in a few things, but it's more or less that's the idea. If you double that diameter, the volume will be 2 times 2 times 2, 8 times bigger. So you can imagine 1,000 times 1,000 times 1,000. The atom has about a billion times more volume than the nucleus, and maybe the nucleus has 1,000 times more mass. That's rather dramatic. But anyway, in fusion, we have two hydrogen nuclei fusion together to form a helium nuclei. They're a special type of hydrogen. Most hydrogen has the most simple nucleus you can imagine, just one proton. The nucleus of an atom is made of two types of particles, one called a proton and one called a neutron. Proton has a positive charge, a neutron doesn't have any charge. Charge, it turns out to be very important because that is what makes the element what it is. You can add a neutron and it's still hydrogen. You add a proton, it's not hydrogen anymore. So it's very important. So this special type of hydrogen that you call deuteron has one proton and one neutron. And if they fuse together, you get helium, which has two protons and two neutrons. Now, why does burning cause energy? Why do we burn things? Well, things, when they get attracted, you get energy out of it. Just like when you're attracted to the earth, you start falling and you have a lot of energy when you're falling, don't you? It's kind of energetic. And that produces heat. Might not be obvious, but if you ever like go down a hill on a car and you get a skid and you got to stop the fall by braking, you might notice that the tires are kind of hot. And like if things rub together, that energy heats things up too. You probably notice that rubbing your hands together keeps them warm. So attracting things together produces heat or energy. Might be a little more complicated. You kind of involve radiation, but I'm not going to get into the details right now. So you get heat out of fusing these things together. Now, like a fire, nuclear fusion needs a spark. Why do fires need spark? Well, anyway, it turns out that carbon is very common. Wood has carbon, coal has carbon, petroleum has carbon. Actually, all living matter has carbon. So really, most living matter you can burn. If it doesn't burn, it's because it's still alive or almost or died recently. It has like a lot of water in it. But if you have anything as dry leaves, dry dead animals, so they're dry enough, will burn. Why don't they burn spontaneously? Why do we even have wood? Why isn't it all burned up? I mean, there's oxygen in the atmosphere, right? Why doesn't it all burn? Well, the atoms generally don't like getting close to one another. They usually don't feel an attraction. They You have to really push them together. But once they get close together, they do kind of attract one another sometimes. In this case, they do. But you got to really push them together. And they say, oh, yeah, I kind of like each other. But you got to push them quite hard. So typically, you don't, to start a fire, you need a spark. You need some heat just to get them together. And then when they get together, you get heat back. Another analogy is you're pushing a car up the hill. You need energy to get to the top of the hill, but if the hill goes down further than where you started with, the car will have more energy when it hits the bottom than it had when you started pushing it. Nuclear fusion isn't that different. You have protons. You have two positive. All nuclei are positive because neutrons are neutral and protons are positive. Perhaps you've heard that positives that likes repel and opposites attract. So since the nuclei are all positive, they repel one another. The electrostatic force repels them. What happens? You get them close enough together, really close. There's another force that takes over, the nuclear interaction. It's extremely short-ranged, but once you push them close enough together, then the force becomes attractive and they crash together. Now, what's the big deal about nuclear fusion? Since it's done on a nuclear scale, the energies involved are like thousands of times greater than energies involved in atomic interactions. They're close together, they really are strong. So for like a kilogram of hydrogen, you fuse that, it's kind of like burning a ton of coal or burning a ton of petroleum. It's kind of cool, ain't it? You can get the same amount of energy for a tiny amount of stuff. So if we can do that, it's a great way of solving our energy problems. That's why people are so interested in it. And fusion has this other attraction compared to the other nuclear type of power perhaps you've heard of, fission, is that it doesn't leave radioactive byproducts, so it's safer. So there's less environmental concern about it. The spark is the big problem. To have a spark to fuel a nuclear interaction, you need a spark thousands of times hotter than when you light a match. You need something like about 1,000,000 degrees or whatever. Not easy to get. You're not going to do that with a lighter. Uh, Up till now, we've only been able to do that with a bomb, a nuclear bomb to start the fusion process. Basically, you have a fission bomb, and that ignites a fusion bomb, and boom! And you can have that happen for a fraction of a second and blow up a city, but it doesn't work very well to have something running all day long and powering in a controlled fashion your lights on your house. So they've been kind of researched. We really would like to be able to control nuclear fusion to have it done in a way that doesn't blow up the street and last for a long time. But that's been a very, very difficult thing to do. You may have heard that the sun relies on nuclear fusion, and it does. But of course, the sun naturally is millions of degrees in its interior. It can do that because it's under tremendous pressure. The sun weighs about a lot more than the Earth does, maybe a million times more than the Earth does, and the Earth is pretty heavy, so you got all that weight in there, so it can be controlled there. Now, how do you keep fusion going? Well, you need about a million degrees to start the interaction, and then to keep it going, you got to keep things a million degrees. So you got to put it in and kind of make a case that won't melt at a million degrees. We got what kind of material doesn't melt at a million degrees? Well, actually, nothing. Actually, nothing will not melt at 1,000 degrees. So it's you can't put it in a jar. So that's one of the big hurdles. Some people have theorized that with very odd magnetic fields, we could trap a tiny amount of nuclei. That's a plural for nucleus, hydrogen nuclei. It might seem irrelevant if you can trap a pill-sized quantity of fuel, but since nuclear fuel is so efficient, if you can just trap something, just a couple of milligrams consistently, yeah, you could power a city on that maybe, if you do that in enough places. But these magnetic fields are super intense, not an easy thing to do, but it's a work in progress. Maybe someday we'll do it. Another possibility is super intense lasers. We're far away from doing that, but maybe it'll happen someday. Last thing I want to say is you may have heard that nuclear fusion is possible because of Einstein's favorite equation, E equals mc squared. Actually, what does that equation really mean? The first time I heard it, I was kind of confused by it because I meant relative to what? C is a big number, but relative to what? Well, it's relative to velocity. Energy normally is 1/2 mv squared, where c is the velocity of light and v is your velocity. So if you're in a car, the energy of your automobile is 1/2 the mass of the car times the velocity squared of the car, which might be like 20 or 30 meters per second. Now the velocity of light is a little faster, maybe 300 million meters per second. So in other words, it's probably like a million times faster. And since you squared means you multiply it by itself, so it's a million times a million or a quadrillion. It's a big number, a huge number. So for our everyday life, it's kind of irrelevant that E equals mc squared is a tiny thing, but in nuclear physics, it does become relevant. The truth is, yes, a helium nucleus has less mass than the sum of two of these deuteron nuclei. It's been measured, and that actually was the inspiration. One of the inspirations for nuclear power in general was some of the people noticed when Einstein published this, that his famous equation, that there was a mass deficit, they called it, that they're not laying up. So if you could somehow fuse things together, it was later figured out rather quickly that that's what made the sun work, and People also do fission, but I'm not going to get into fission right now. Atom splitting, I'm not getting into that right now, but it inspired the idea. You might wonder, does E equals mc squared apply to burning wood and coal? You might be surprised by the answer is yes, it does. A carbon dioxide molecule does indeed have less mass than the sum of the mass of an oxygen atom and another oxygen atom plus the carbon atom. Those three atoms combined have more mass than the molecule. The difference is, since it's 1,000 times less than the mass loss of fusion, it's not very measurable. It's kind of hard to measure. And in fact, I think before Einstein published it, no one had ever measured it. It never occurred to anyone to measure it too, and it just wasn't noticeable. Even now, it's very difficult to measure, and that's why you don't hear about it very much. But yes, E equals mc squared applies to all physical interactions. There's nothing special about nuclear fusion in general. Well, have a good day. Bye.